Okay, so here's the second half of the video where I go through the document and help you with the questions. So again, here is where the seed length and quantity at that length, this would be class data, would go. And then build your graph. Again, the seed length in millimeters, that's going to be your y-axis. And the quantity at that length, that's going to be your x-axis. And then here's my data. So you're going to build your own, of course, but here's the one that I built. And it is what I would call a normal distribution curve. Also called like a bell curve, a normal distribution curve, kind of shaped like a bell, I guess. And we will have to take a look at this with the data analysis. And so draw a red vertical line through the graph from top to bottom at the mean. And so it would be a pain to have to calculate the mean, but I had a spreadsheet do that. And so the mean is 16.7 roughly, just rounded to the nearest tenths of a decimal. So 16.7, draw a vertical red line. Okay, and again, the mean, I'll just write x with a line over it, that's the mean. So that means that half of the data points would be on either side of that red line. Number 2, draw a blue vertical line on each side of the graph for 1 standard deviation. Okay, again, the standard deviation would be a pain to calculate. It's on your formula sheet, and it's listed. Standard deviation is the square root of the sum of each data point minus the average squared divided by the sample size minus 1. So you'd have to do that calculation for each seed measurement. Like you'd have to do that for the seed that measured at 12. You have to do that for the 5 seeds that measured at 13. So you'd have to do that calculation just a ton. So in APBio, you'd have to do the calculation, but you have to be able to work with the concept of standard deviation. So what is 16.7 minus 1.6? That'd be 15.1. So we'll need a blue vertical line at 15.1. And again, that represents 1 standard deviation in that direction, and we'll also need 1 standard deviation in that direction. So, let me just get my calculator out, make sure I do this right. So we have 16.7 plus 1.6 is 17.3. So at 17.3, I did not do that right. At 18.3. Oops, my bad. 18.3. We have another standard deviation. Okay, so what that represents is between, oops, there we go. Between those two blue lines lies 70% of the data. Plus or minus 1 standard deviation is roughly 70% of the data points would fall in this shaded part of the graph, and then this shaded part right here and there on the other side would be the remaining 30%. So 70% is there. And then if we do 2 standard deviations, it says to use a green line, I believe. Okay, green vertical line. So then we're going to basically go and double. 2 standard deviations is 3.2 because I just doubled 1.6. So if I take the mean, which is 16.7, and I subtract 3.2, that means I'm going to put a vertical line in at 13.5. And that represents 2 standard deviations this direction. And I'll do another one. I'll take 16.7 plus 3.2, 19.9. Okay, roughly there. So that means, so the 2 represents the space between the green lines there, represents 95% of the data. And we could go on, we could go a 3rd standard deviation, which would represent 99% of the data, and so on. So that's just saying that 99% of the points will be between, of the seeds that you measure, will be between 13.5 and 19.9. at that, and that you will get a few outliers. About 1 out of every 20 will be either there or there, but most of them are going to be, 95% of them will be within the green lines there. So 2 standard deviations is what we typically look at for data analysis. Okay, and then you can calculate the standard error of the mean from that. It's a more simple equation, so standard error of the mean is very, very similar to standard deviation because it starts with, the equation includes the standard deviation, but we're not going to do anything with the standard error of the mean. So for number 4, explain how your normal distribution or bell curve of seed variation data would change under the following selective pressures. So in the book here, we've got chapter 15, and so I'll just scroll to page 300. Okay, so specifically looking at concept 15.4, where we have various selective pressures, the first one, stabilizing selection, would be resulting in a move towards the average. So if the extremes on either side, if the seeds that were really smaller or the seeds that were really larger tended to not survive and reproduce, assuming it's genetically inherited trait of seed length, then we would have more and more individuals at the mean, and we'd still have a bell curve or normal distribution. It would just be taller at the average, and there would be less at the extremes. And it does give some examples. An example of this type of selection would be looking at birth weight. And so it's a tough one to talk about, I suppose, but babies that are born, it says in this graph here, that are between 4.5 and 9.5 pounds would be kind of most of the individuals that would be born there, and the mortality of those individuals is pretty low. But as you go out to those extremes on either direction, the mortality increases, and so that kind of basically influences, it's a stabilizing selection that influences the birth weight to be near the mean, which would be right around 6 to 8 pounds. So the second question was what if it's directional selection? Directional selection will move the average to one direction or another, and this is just showing a move towards the smaller side of the scale. So you'd still have a bell curve, but if the seeds that were smaller, for instance, tended to survive, then the average or mean would decrease over time, because the seeds that were larger, for instance, would maybe not be surviving. And who knows, that we're just talking scenarios and situations, but that's an example of directional selection. And again, the book talks about directional selection with longhorn cattle is that, adults with longer horns were more able to protect their young, so their young had a better chance of survival. So directional selection resulted in longer horns on cattle, and just versus shorter horns. And the third was, what if there's disruptive selection, which is kind of a weird one to think about. That's where the extremes do well and the average doesn't do well. And that sounds kind of weird, why would that happen? So there's an example in the book about that too, a species of birds with either very more extreme smaller bills and more extreme larger bills tended to survive because of the food source that was available. Smaller billed birds could feed more efficiently on soft seeds, so they tended to survive and do well. Larger billed birds tended to be able to crack open the seeds that were available that were harder, but individuals with medium-sized bills didn't do very well because, they didn't have a seed source that worked for their bill size. And so that's an example of disruptive selection. So I'm going to pause the video and create a new one here for going through the results for part 2, natural selection.